All right. Today we are going into chapter 22, section 3. Um, and we're dealing with more functional groups. So a few more functional groups that we're going to talk about. But all of these functional groups have one thing in common. And that is they all have a carbonyl in them. So these are carbonyl compounds. And when we talk about carbonyl, really all we're saying is there's a carbon with a double bond to an oxygen. So all of our functional groups today are going to have that somewhere in there. Carbon, double bond, oxygen. So our first functional group, remember we can write them all as general formulas. Actually, our general formula is that. Now the star, that's the first time we've seen the star in the general formula. And what a star means, it could be the same as R. It could be that there's a carbon chain. Or it could just be a hydrogen. So you can see CHO. So we've got this carbonyl, which is the C and the O, and we have to have at least one hydrogen there. So this is the structure that we're looking at. And over on the other side, it could just be a hydrogen. This is a valid molecule. Once again, you'll notice carbon only has 3 different atoms that is attached to, but it still does have 4 bonds. Remember, carbon needs 4 because 2 of them are there. So 1, 2, 3, and 4. But like we said, we could put another carbon right there, or we could keep going. Now we can't replace that hydrogen with a carbon. That hydrogen has to be there. And so that tells us that this functional group, the aldehyde, that's what this is, that carbonyl has to be at either end of our carbon chain. So if we have, we can say we have 1, 2, 3, 4, 5. Okay, so we have 5 carbons there. If this is an aldehyde, we have to have that carbonyl group. And I don't always put that H right there, but I wanted to point out that yes, there is a hydrogen there. But remember, anytime we're doing these, if you can put a hydrogen anywhere, you do. But anyway, that carbonyl group has to be on this side or this side. If we put it here, it's not an aldehyde. Now we can put it there, and in fact, we're going to talk about that next, but it's not an aldehyde. And that actually makes things nice, because since you know it has to be on one side or the other, it makes our numbering really, really easy. In this situation, we would start right here. 1, 2, 3, 4, 5. And so, how do we name this? Well, we have 5. So we have our prefix. And we are going to keep the AN, like pentane, but this is an aldehyde. And so we add an AL for that. This is pentanal. We don't have to say it's one pentanal. We don't need to do that because, once again, as we've said over and over in chemistry, if we can get away without writing something because it's just, it's the only possible thing, or we can assume something, we're going to do that. Right there, the fact that we have Al for aldehyde tells us the carbonyl group is at the end. It has to be at the end. And so it has to be 1. Of course, we can branch these as well, just like we can with all of our other things. So if we put a methyl group right there, that is carbon 3. So this would be 3-methyl pentanal. Okay. Anytime we have a branch chain, it's going to follow the same rules that we've already established. Okay. The difference is the functional group becomes the most important for numbering. Becomes the most important. So we number off of that, but we really don't care about anything else. The numbers just fall where they fall. And yeah. Okay. We do see ring structures with these sometimes. So here's our functional group, and we have that ring. This it's going to be carbon number 1 and all of that. You might run into these on the homework. I don't remember if I assigned any of these. Let me just double check. I typically don't really put this on the tests. I don't do many ring structures on the test. Yeah, looks like it is just 1. It's easier to look if I look at this instead of the book. Okay. Yeah, it looks like there is 1. Now, the reason why I don't give a lot of these because it's a little bit different. Because yes, there are 7 carbons, but remember the ring structure is going to be our parent chain. So this is cyclohexanol, even though we do have that 7th carbon. It can be a little bit confusing, and that's why I personally don't give too many, and there's only 1 on the homework. So anyway. there are a few examples of ones that you may be familiar with in the book. So if it's just one carbon, okay, that's methanal. We have this. One carbon, methanal. Right? That has a common name of formaldehyde. Formaldehyde is what we can use to preserve these specimens. So there's actually that brittle star in there. I'll be able to really see it. But the formaldehyde stops bacterial growth, and so it doesn't decompose. Also, it does have one in there called cinnamaldehyde. Cinnamaldehyde is what you're smelling and tasting if you eat cinnamon. It has a benzene ring and an alkene in there, and so there's actually a couple things going on in there. But anyway, so that is the common cinnamaldehyde. Okay. Our next functional group. This one, actually reuse this. Remember we said we're going to bring that carbonyl off of the edge into the middle. So what we get is another R prime, just like we saw with the ethers. Okay, so that means we have to have carbons here. They can't just be hydrogens. Because if one of these was a hydrogen, it would mean it was on the end, and that would be an aldehyde. But since we have at least one carbon on either side, that becomes what we call a ketone. Ketone. So how do we name these? Okay, so remember, we can't put it on either of these, but if we put it right there, now we can look and say, okay, 1, 2, 3, 4, 5, 6, 7. You know, we're dealing with het. We do keep the AN and then ONE. This is heptanone. But now we have to say where that functional group is. Because we can put it here, 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 or here. And those are all different isomers of heptanone. So once again, we have to do our numbering scheme. Now we can go starting here or starting there, either way. And so we pick the number that is going, which one is going to give us the lowest. Now, pretty obvious if you are looking, we're going to start on this side, okay? Because that's 1, 2, 3 instead of 1, 2, 3, 4, 5. So this is 3 heptanone. Just like always, we can put branches on. And same rules as before. It might help if we do this, whenever you are naming, it helps you to write out the numbers, write them out. So we have a 2-methyl, and 4 and 5, we both have ethyl. So we need to put those in the name. We got to get them in the right order. Remember, ethyl is going to come before methyl because E comes before M. It's alphabetical. So we're going to put our 2-methyl right there, and then 4,5-diethyl. So what that molecule becomes is 4,5-diethyl 2-methyl-3-heptane. Okay. An example that you might be familiar with, acetone. Acetone is, well, the official IUPAC name is 2-propanone. Now, the book does list it as 2-propanone. I imagine there are plenty of people who would say you could leave off that 2, because if you put it anywhere else, it's not going to be a ketone. It's going to be an aldehyde. Anyway, acetone, it's in different products. It can be, you find it in things like nail polish remover. It's a really good glass cleaner. If you ever have glass that, for whatever reason, has something on it that just your normal glass cleaner isn't getting, acetone actually works really, really well. You just got to be careful. Like, it's glass in a mirror that has some wood finish around it. Acetone will melt the finish that they put on the wood. So you got to be careful with it because it dissolves a whole lot of stuff. Anyway, so, all right. So here we have another star, which, remember, can be a carbon chain or it can just be a hydrogen. When we see this, this is a carboxylic acid. Carboxylic acid. It is an acid. This hydrogen actually can dissociate, and yeah, so it does have the properties of a true acid. When we name these, once again, okay, you notice we don't have RR prime, and that means this has to be on either side. We cannot put this in the center. Can't put this carboxylic acid in the center. So with numbering, that's great because it allows us to know we have to start wherever this is. So we just that up there. We count. This is carbon 1. Go the rest of the way. We have 6 carbons. So we know we're dealing with hex. Just like always, we do keep the AN. Then we say OIC. And there is actually a space here. 2 words, acid. So hexanoic acid. Branching, again, works just the same. So we have methyl, methyl, methyl. So we have 2, 4, 5. Tri-methyl. 3-ethyl. Okay, so this molecule, 3-ethyl, 2,4,5 trimethyl hexanoic acid. Examples. One thing is formic acid. And it gives the example, you know, there's pictures of ants here. Some ants are able to spray this nasty venom, and one of the components is formic acid. Formic acid, the official IUPAC name is methanoic acid. So since it's methanoic, you know that there's only one carbon. So that is what we have. So sometimes if you are seeing the condensed structural formula, instead of writing it out like this, you'll see it written as that. So if you ever see anything that has the COOH, that is a carboxylic acid. Okay. So there's that. Now I will mention, up till now, all of these can have multiple functional groups. Okay? I actually, you know, a valid compound to throw another one over there, or you know, we could have multiple ketones, or we can have aldehydes. Okay, we can do that. Okay. We even are allowed to mix them. So you can have this carboxylic acid with the aldehyde. Okay. If we wanted to, we could throw a ketone in there. We can mix them. I'm not going to do that to you. The book doesn't do that to you. So we're not going to take the time to go over the rules. There is a hierarchy of which one becomes the actual functional group that gets named, and then the other ones, there are different ways that you throw that in there. Just want you to be aware of that. Like I said, I'm not going to give it to you on a test. The book doesn't give you these mixtures. Okay? Just know that they do exist. All right. We're down to our last couple of functional groups here. The next one is what we call an ester. And just like we took the aldehyde, which had to be on the end, and then moved it into the middle, now we're going to take the carboxylic acid and move it into the middle. So now, instead of an H, we have an R group. Now that still is going to stay a star. That, we don't have to have any more carbons than just that one, but we can. Over here, however, that has to be a carbon chain. There has to be at least one carbon with hydrogen, but it can be one. So an example Okay, so we've got that. Now, just like we had with an ether, we have two carbon chains that we have to deal with. Now, with an ether, what we did was, okay, count them up, whichever one comes first alphabetically, that's what we're going to put first. This is a little bit different. With esters, we have an absolute parent chain. It has to be the parent chain. And the way to find that is find the carboxylic acid. So if you take off a carbon chain and you're left with the carboxylic acid, that is the parent chain. So we take these carbons off, and it looks just like a carboxylic acid. That is the parent chain. We took that off, well, we lose the carbonyl, and it just, it wouldn't work. Right? So you find the carboxylic acid, that is the parent chain. So here we have two carbons in our parent. So that is F, the two carbons, ANOATE, ethanol. And then over here, we just described how many carbons we have. So 1, 2, 3, 4. So this becomes butyl ethanol. So this one isn't exactly like the ethers where we, just count them up and put them in alphabetical order. We have an absolute parent chain over here. But over here, we count our carbons. We put that. If we added another one there, that would go into propanol. This brutal propane. So, esters. Esters are, well, we find them a lot in nature as flavor compounds. In the back of the room, there is a poster with a bunch of esters and what they actually smell like. Butyl, butyl propanoate, that looks like an apple. Okay, so that would give you apple. Butyl ethanoate actually looks like it's apple as well. So as it turns out, there's a lot of similar compounds that we see in a lot of these natural flavors. It's not typically just one. But yeah, so there's a bunch of different smells on that poster that you can look at and see. Anyway, esters, very common to be associated with some sort of smell. All right. This is our last functional group. Amides. Our general formula, like we've been writing, it actually looks a whole lot like an ester. We start with our star. We have our carbonyl group. Okay. But now, instead of going into a carbon, we have a nitrogen. So it's going to be one hydrogen, and we have another star. This can be, like we said, either a hydrogen or another carbon chain. On the test, I will make this a hydrogen. It just makes it a little bit easier. It's not that you couldn't name it. It's just one fewer thing for you to memorize. So we'll just change that. For our class, this is what we're going to consider. Okay. But be aware that, yes, we can replace one of those hydrogens in the real world. So, when we name these, well, let's do an example. How many carbons do we have? Once again, we start with this carbon, 1, 2, 3. So we know we're dealing with prop. So we still use the AN, and then right. So this is propanamide. Probably the most well-known is the acetaminophen. Acetaminophen is otherwise known as Tylenol. So, and that actually does have one of the hydrogens substituted. So we got 2 carbons on the one side. And we've got, and then it actually just goes into a benzene ring. So that right there, it's Tylenol. So that is our last functional group. Okay. Now, there's one last little thing that the book sticks into section 3. That's a specific type of reaction. Now, section 4 gets into more types of reactions. So I'm not sure why they put it in this section instead of just lumping it with the other ones. But anyway, since it's in this section, we'll discuss it with it. It's called a condensation reaction. So a condensation reaction, what is happening is, well, let's say we have I don't even want to draw everything out. What we're going to do, we're just going to use R. And then we have a different alcohol. Okay. Could be the same, but anyway, what can happen so H2, so we can actually generate water here. So what's going to happen is we're going to take these 2 alcohols. Now we've lost all of that, all right? So keep this oxygen with R and R prime. But what we've actually developed is an ether and water. So condensation. Oh, condensation because you get water. The example that it gives in the book, remember how we said we can combine these different functional groups? It has a combination here. So instead of this being an ether, it's actually a carboxylic acid because of one of the functional groups on there. But it is acetylsalicylic acid, which is what we call aspirin. Anyway, so there are the functional groups. That is section 3. Next time, we will talk about some more types of reactions, and we'll also get into polymers. But we'll stop there today, and let's get started on some homework. Just 4 problems.